Second to last Friday. All right, I owe you a study guide today that should be coming out sometime before 1 o'clock. That's basically my deadline to get that out because I will have my game dev lab followed by a department meeting after that. If I don't get it out before that, I don't know when it's going to get out. So expect it by 1 o'clock. I know that Grader is still behind a bit on, we're going all the way back to sequence alignment, not fully being published at this point. I'm not really okay with that level of delay at this point. So I'm working with him and I'll step in as I need to make sure that that gets turned around and to you. This assignment that you just submitted and or submitting tonight is also needs to have a fast turnaround because I'm going to be releasing the new assignment for that. It's fully designed and ready to go. It just needs the grader's approval for grading and API results. I can describe a bit of it, perhaps if there's a little bit of time at the end of today's class, and motivate why the structure is the way that it is. Basically, since we cut design patterns, I've been attempting to incorporate design patterns into the labs that I designed. So that's why the facade was there in the last assignment and why there will be a strategy in this one. But I think that it ties very well and makes everything we're doing here very scalable in a way that you can show off and is useful beyond just the scope of the algorithms that we've covered in class. So I recognize that there's a lot of feedback that you are waiting on. Something I am aware of and actively working with the many other things that I'm doing to try to get to you in a reasonable time frame. So I do apologize for the lack of timely feedback. That's not ideal. Something to study to learn design patterns. Yeah, so if either you took the design patterns course, it was heavily used there, but Refactoring Guru is a fantastic site for that. The image of the facade on the first assignment came from that site. I can quickly pull it up and paste it in chat here for those of you who are on Zoom. For those of you who are here, Refactoring Guru is a great place to go find a bunch of, we have a little bit of time, I'll just bring it up here. You don't need to see my master's student's thesis. Although if you took 211 from David Sergio, he is finishing up his thesis, which is this thesis. I get to read that over the weekend too. So if I haven't shown this to you yet in this class, I forget if I have or not, but it's a fantastic source. I don't know of too many other sources that are this good for training object-oriented design. So the two pieces of it are the refactoring and the design patterns. As I'm designing a sequel course to software engineering, I want to go through a lot of the refactoring techniques that we have in object-oriented programming. So the really important ones, things like organizing data and simplifying method calls, dealing with generalization. All of these are tools that you should be aware of within object-oriented programming that will help you to produce scalable code that adheres to the single-use principle. Basically, you can go over all the solid principles through the use of this, and it is a frequently discussed concept of interviews for object-oriented programming interviews. On top of refactoring, how do you turn gross code into better code or code that does not scale well into code that does scale well? You can imagine as a motivation to this that You are starting an internship, and the code that you are working on that's already been produced is one that you have to interface with. But in order to make any changes to that, you have to change the existing code. That means you need to read and understand what everyone who came before you did and designed and implemented. Some of those people may not be at that company anymore. Some of those people might be there, but not really want to go back and look at their old code and give you a half-assed answer. So ideally, design means that you don't have to go back and change any existing code. You can just add new code and interface it with the existing code in a way that doesn't require you to change any of that existing code. So refactoring techniques will help you to be able to take code that is not particularly well designed and scalable and turn it into code that is well designed and scalable. Design patterns are the way to produce that scalability. So if we look at the structural patterns, that's where our facade comes from. And you will see that this will look very familiar.
Yeah, you put that in the assignment.
Yeah, this page was exactly where this came from. And we're going to be using the strategy behavioral pattern in the next one, as soon as this
Fascinating.
loads. So this is an easy way to see, where is this? You're going to take some existing, basically there are a bunch of different algorithms that could solve the existing problem. In this case, it's the searching algorithms that we've done. If you wanted to know the shortest path between nodes A and B, we have a bunch of different ways of doing that. We could call Dijkstra's, we could call Bellman-Ford, we could call Floyd-Warshall. But we don't know which one to call without further information. Are there negative edges in the graph? What is the query? Is it a single source to single destination? Is it every source to every destination? We don't know what the appropriate search algorithm to call is until we understand the query and the underlying structure of the graph. So we are going to compose our directed weighted graph class having a field of an interface that we're going to create called search. And we'll use polymorphism to determine at runtime which algorithm to implement. When I query and I say I want to search and I want to find the shortest path between A and D in this graph, then inside of the search code, I can figure out, okay, is there a negative edge weight in this graph? If there's not, it's a single source, a single destination, so I should call Dijkstra. Now, at runtime, after this query has come in, we can compose, we can say that this search interface variable now will become a new Dijkstra object that then implements Dijkstra on this graph. If there were a negative edge weight, we would have composed it with Bellman-Ford instead. But again, from the API's perspective, from that end user's perspective, they don't need to know that. They don't need to know anything about that there are different search algorithms. They just need to know, I want to find the shortest path. They don't need to know when Dijkstra's or Bellman-Ford applies. They don't need to know, is there a negative edge weight in my graph? Ask that question and need that as part of their call to this code. The code handles it underneath the hood for them. The way that I've been describing this to people in my office is it's very much like how much you need to know in order to operate a car. You don't need to know very much to turn on a car and to know shift into drive, press gas pedal down, car go vroom. There's a lot more happening underneath the hood than that, significantly more, but to operate the car, you don't need to interface with all of the mechanical complexities. So part of the reason of this two-parter assignment is that that's what you're creating. You're dealing with the internal complexities so that when someone uses your API, they don't have to worry about or know any technical details about graphs, about searching graphs, so that it's as easy to use as possible, as streamlined as possible from the end user's perspective. You, the designer, know that, but you, the future person who's using this API, won't need to remember it in order to use it. You, when you publish it for someone else to use, they won't have to know anything about that in order to use it. They just need to know, I want to find the shortest path between these things, and your code will say, okay, and handle the rest of it for you. So that's the beauty of design patterns. As well, you can imagine that there is an additional search algorithm that you want to incorporate into this in the future. Instead of having to go modify anything about your directed weighted graph class or any of the existing search algorithms, you just write one new class, implement the search interface, and now it works with your directed weighted graph. There is no other change that needs to happen to your underlying code in order for it to work. So your API is scalable in that regard. You can release new features, new search algorithms, and it will break no one's code who is currently using your API. So all of that is built into the design of these last couple of assignments. So the assignment you're submitting and the assignment that you are going to be starting. All of that went into designing this, but I just thought that I should let you know of this source because there are plenty of other design patterns that do many other useful, scalable things that you may want to go look at some point. Very useful. All right, I didn't even get through announcements before getting sidetracked, which is great. It was a very good sidetrack. Any questions on any of that, or why or how, or I can address anything before I go back to announcements?
Go ahead. I think we did another thing.
Good.
It's wrong though.
So I have a study guide coming to you. We're getting assignments to you. There will be an exam a week from today. We'll be studying for that next Wednesday and Thursday. Monday and Tuesday, we'll be going over interviewing. Pending a little bit of time today, I can get started with that. And I think that's just about everything, aside from recognizing that I want to get feedback to you as soon as I can.
I'm sorry, I'm thinking to myself, sorry.
Yeah, no final exam, just a last exam that may have a few higher level cumulative components. Yeah, we're getting both the assignments out today so that you have the weekend to work on them. And the book problems we do next Wednesday, and the final
As in the
part
book,
two of this.
as in the book homework problems you gave us.
Yeah,
Oh boy, I got one.
then the final implementation project of that strategy design pattern and the implementations of the different graph search algorithms will be due over finals week in place of a final. I would much rather give you a project to work on rather than a cumulative exam. Any questions, concerns, clarifications on anything about the remainder of class? Okay. We'll dive back into the very last bit of approximation algorithms. We only have a few slides left of this. Yeah, there will just be one assignment due over finals. I don't want to overload you when you're already doing other work with other finals and other projects. That would not be fair. That said, it's going to be a fairly bulky assignment with a lot to it that ties into your existing assignment. So you may spend some of the time for that last assignment reworking some of the internal components of your directed weighted graph, just because it will help make the design for this second part easier. You might find flaws in your design. You want to go back and modify that to make it better. Yep, just that last assignment. And that'll be the end of the class. I do want to note, I guess there was a couple other random announcements I can make. There will be next Wednesday an exposition of all of the electrical engineering capstone projects from 12 to 2 down in the Catalyst lobby, and all of my game design students will also be down there showing off the games that they made, as well as there will be another games party. I want to call it a party because it kind of feels like a party where people can come play my game dev students games next Friday from 4 to 8, just like there was a few weeks ago.
Nice.
So there will be food, there will be games, there will be fun. It's a good way to de-stress ahead of finals week. So hope to see people there for that.
I would actually like that. Actually, hey, one thing I want to say about the last one, I actually enjoyed a lot of the games that I played. There was only one game that when I was there that I did not play, but all of them were pretty good. I just had a lot of trouble trying to figure out how to play and pass, and some of the game mechanics were a little annoying in some areas, but
Sure.
um
I think we may have even made better games this time.
I think they did a pretty good job
They
with the
did a
game.
great job last time, and
Yeah.
I'm very proud of the work that I've seen so far. So that will be very fun. Again, hope to see you there. I'll have Magic available as well. Okay, let's dive back into this. So we were talking about the traveling salesman problem, which again is, imagine you're a traveling salesman trying to sell your wares in a bunch of different cities. You start in one of those cities. You must visit every one of those cities and end back where you started with the minimum possible path, total path length between those cities. So we talked about using a minimum spanning tree as a potential for approximating it. Doing some kind of depth first search on that minimum spanning tree seemed like an interesting idea. So let's take a look at it. Doesn't quite animate it correctly. No, I didn't bring these up. Okay, so here's a graph. The minimum spanning tree on that graph might look something like this. A depth first search or pre-order traversal, same thing, of that minimum spanning tree would look something like this.
Yeah, you're very right.
So we could use this concept of the triangle inequality to find a shorter path where we do something like from B, we go to C, back to B, and then to H. That forms a triangle where we could look at the part of that that is C to B to H. And if there exists an edge from C to H, we can use the concept of the triangle inequality to look at, is the path from C to H shorter than the path from C to B to H? If so, then we can take this guess, the pre-order traversal, as an approximation for the traveling salesman problem and replace the C to B to H with a direct C to H. We could then look at H to B to A to D, and is there a better path from H to D than H to B to A to D? If there exists a straight path from H to D, we could just take that. So we end up with an approximate solution that looks something like this.
Well, okay then. That's fascinating.
You can see where we use the triangle inequality here. We used it from C to H. We used it from H to D. We used it from F to G. And then we used it from G all the way back to A. Is this an optimal solution? Probably not. We can see that we're crossing our paths a few times. An optimal solution would probably look something like this. But to come up with that optimal solution, we would need to look at every possible path between the vertices we visited and the vertices we haven't visited so far. And that is just as intractable. It's another version, that's a smaller version of the traveling salesman problem. Since the larger traveling salesman problem isn't tractable, the smaller version of it also won't be tractable. But we get an approximate solution that we can again bound to, because of the triangle inequality, twice the length of the optimal solution length. There's one other condition that we need to talk about. If there's a shorter path by the triangle inequality, as long as the cost function satisfies it. This just means that we're not just looking and doing this no matter what. We're not making these shortcuts no matter what. We have to make sure that the cost function satisfies that triangle inequality. What I mean by that is that we talked about how the triangle inequality works in general. You have a triangle with 3 endpoints, and no matter what this triangle looks like, the sum of 2 edge lengths is going to be greater than the third edge length by the definition of a triangle. But in a graph, we place edge weights on this in a way that the triangle inequality might not be satisfied. This could be 1,000, and this could be 6 and 4. And 6 plus 4 is not greater than 1,000. So we have to verify that this triangle inequality actually holds before we just assume that the path from C to H is going to be shorter than the path from C to B to H. That's not necessarily going to be true, but wherever we could potentially replace that, we'll just look at, does the cost function satisfy the triangle inequality? If so, then we can replace the two-edge process of the preorder traversal of the minimum spanning tree with a direct edge in our Hamiltonian cycle.
Yeah, wow.
So that's the basic idea of forcing here the cost function to satisfy the triangle inequality for that preorder traversal of the minimum spanning tree. So you'll see that there's a reason we study all of these tools in algorithms. It's so that when we see a problem like this, we can start to recognize that we can come up with an approximate solution that uses a tool that we've seen before. And that's how a lot of state-of-the-art research is done in algorithms, is to recognize this problem relates to another problem that I've seen before or studied before or can make on the spot in a way that allows me to come up with a new solution to this problem with new bounds that may, in certain situations, be an improvement on the existing state-of-the-art solution. You don't necessarily have to, as an undergraduate, go reinvent the wheel and go produce new research like this, but the more you understand the tools and how the tools relate to each other, the more you can see how those tools are related, especially when given a problem that you haven't seen before. Someone came up with this. Let's see, would we change it? We knew the weights represented real space and literal traveling salesman. Yeah, in this case, we would know that triangle inequality is always true. So if you're modeling real space, then you absolutely can use, the reason I bring up the triangle inequality is because if your graph does represent real space, then you can use the triangle inequality and you don't need to ask the question, does the cost function satisfy it? If we're modeling real world space, then that will always be the case. Although there's a little bit of strangeness to this in that if you're dealing with anything like the surface of the Earth is curved. And that can create some, when you're dealing with 3 dimensions instead of 2, it scales a little bit differently. And you can come up with some, you just have a little bit of extra verification.
Yeah, but you have a good point.
Unless you're a flat earther. That just makes everything easier. If you live in a world that doesn't exist, the world is easier. Surprise. Why not one-dimensional? We could make the Earth one-dimensional, and then it's even easier to calculate things. Zero-dimensional. You don't exist anymore, and your opinions aren't valid because you don't exist. All right, we have one more problem we want to cover past the traveling salesman. This is the one with the most complicated solution, but I feel like has the most interesting thought process surrounding it. So we're going to look at the subset sum problem. And the subset sum problem says, given that we have a set of positive integers and a target integer sum, we want to determine whether there is a subset of that set such that the sum of those numbers directly adds up to the target integer that we're trying to find. So you can imagine that the set contains 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we want to figure out if there is a subset in there that adds up to, I don't know, 15. And the answer would be yes. 1 plus 2 plus 3 plus 4 plus 5 is 15. As is 10 plus 5. There are multiple ways to do it, but there is at least one way to sum up some subset of that set in a way that sums to the target sum. There is an optimization problem that we see frequently out in computer science. That is, return the closest value less than or equal to that target value. So this would be something like you want to load packages onto a truck, and the truck has a maximum capacity in weight. And we have a bunch of boxes that weigh a certain number of pounds. What combination of boxes should we load onto the truck such that we get closest to the truck's maximum capacity? You might not get every single box on the truck, but we can get the most onto the truck that we can so that what's left over has the minimum weight, and what's on the truck has the maximum weight. So you can imagine again that even though we display this as a pure math problem, there are many applications out there that are useful and are applications of this problem. So what would an exact algorithm for this be? Let's say that we're interested in coming up with an exact answer. Is there a subset that sums to exactly t? How would you do it?
Well, that is actually an incredibly good question. Well, if we're going with a set of positive integer target sum that is not negative for obvious reasons. Well, in theory, it is possible.
Any ideas? Be a good approximation if we had some running total or sum that we just look at the next element, and if the next element doesn't cause us to go over that threshold, we add it to the existing set.
Yeah. Yeah.
Is that guaranteed to give us a subset that sums to t if one exists?
No,
No. That would work sometimes.
not all the time.
It's a good idea for a baseline. It's a really good idea for a baseline for an approximation algorithm. What would a brute force algorithm look like?
Going through every number and adding them one at a time until.
Every possible combination of boxes.
Yeah.
How many combinations of boxes are there going to be?
Let's. If there are like n combinations of boxes, or I should say m in this case. Like, there are numerous of them, all the way up to.
Let's think of it this way. For each box, the box is either on the truck or not on the truck. Does the fact that one box is on the truck cause the next box to either, did that change whether the next box can be on the truck or not on the truck? We're looking at every possible combination. No, it does not.
No.
They are independent. So there are two options for each box, 2 to the power of the number of boxes. 2 to the n.
Okay.
Look at that. The variable is in the exponent. This is worst case exponential. And so indeed, this is an NP-complete algorithm. It's an NP-complete problem at the moment, unless we can come up with something that is better than that. And in fact, I can tell you that it's NP-complete. And if we could find a better way to do this for the exact target, then we could solve every NP-complete problem because there is a polynomial time reduction from this to every other NP-complete problem.
Well.
So again, just like we've done the last couple of times, let's break into some groups and try to come up with a good approximation algorithm. So given that we can't figure out whether we can get exactly t, can we come up with an interesting algorithm that gets us as close as we can get to t, but ensuring that the algorithm that we invent here runs in polynomial time?
And amazing.
Let's talk about it for a bit.
on.
Does the fact that you needed it to exactly T and not like some you make it incomplete, is it the exactness?
It's, yeah, so the approximation algorithm that I will show you will guarantee that we can get to within X% of T. Given bounds that basically we're trading off the amount of work that we're doing for how close we can guarantee that we can get.
Oh. Great. Locked up. All of me. Oh. And. That's that.
Yeah, it would be close enough. My first, it is, this. Hit the box of it.
Possibility, but there's also the fact that, we're that one, when we're starting in reverse order, it's not a bad idea. So, possibility that n could be greater than c.
Yeah, and then you say like. If in and goes over T, then don't have that, and shoot. Keep staying on T.
Well, actually. Actually, I like your idea, but I think we, so I think we flip the, if.
Okay.
That's it. Well, I don't mean we flip what this purpose is, we flip it, but it only works if, and is less than or equal to t. What do you think? Or sorry, or, I mean.
Exactly.
Yeah, so entrepreneur phrase, entrepreneur phrase.
Yeah.
So it's gonna get that as close as we can get to T without going so.
Well, in this case, if we're gonna try loading package subs on trucks, yeah, the best place for us to start is start the heaviest boxes in there, because. Smaller boxes will be stacked on top, will be crushed.
Luckily, that is not part of the problem, but if we're actually doing it in practice, that is an additional constraint we need to consider.
Yeah, I have a lot of experience loading packages onto a truck. And unloading them, by the way.
Mhm.
Yeah. I'll tell you later. And so basically we need to figure out the. Integer and. As for like. So let's see, say whatever the heck the number is. If it's greater than t. Oh, yeah, if it's less than or equal to t, we put it in, if not, we. Skip over.
Yeah, and then what would you choose? Is there an order for like after choosing?
Well, if I'm gonna be honest, I actually am not sure. But I think that for subtraction, we basically was just, we just store that number, somewhere else for the sake of, I would wanna store it, and I would also. And then we subtract, and targets of t by that number, and then. And then continue to see into the next number is. Plus then I used to see that twice, then, you know. You're involved with this?
Yeah, it's just kind of like this. Is there a box and it's a sharp way?
Yeah.
I'm thinking of like, choose the largest one of this first. We can do that. Drawing things, like, if like 10 goes over, then it's the bottom.
Yeah.
So it's not possible.
Let's see, that piece, yeah. This really definitely fit this area, but I see what it is. but 31. Oops.
Any ideas? We've had a few interesting ideas online. I'd like to query the class as well. What have we come up with? Any ideas?
Well, we have a good idea. What do you think? Okay, well, I'm just trying to see if I can have a different perspective.
Our idea
Takes like a picture.
is that you pick out of like the set of boxes, you pick the largest one that fits. You put them in order, like largest to smallest. Pick the largest one that fits, go in. The one doesn't fit, skip that one and see if the next one fits.
Okay.
I at least think he has the right idea,
That is certainly interesting.
but we don't know exactly what the heaviest boxes are gonna be in the box.
Yeah, this maps very interestingly onto the knapsack problem that we looked at earlier in the quarter, where we were thieving different amounts
I
of
remember.
value and trying to shove weights into a knapsack. If the knapsack is the target, we want to fill the knapsack as close to full as we can get it. There was an additional problem to that was the value of the item compared to the weight. Here we don't have a value of each box to consider, but it is very close to that problem. So we could use something like dynamic programming, where we could come up with values that are sums of 2 different boxes and 3 different boxes and 4 different boxes. And if we stored the solutions to those sub-problems, then we could look at, if we're looking to optimize a 3-box solution, it would be a 1-box solution plus a 2-box solution, of which we've already calculated that. So that would be a very interesting way to come up with a polynomial time solution to this. And it's not a bad idea.
It's like the rod thing, right?
Yeah.
Yeah, it is.
So I'm going to present something that's a little bit different, because we want to be able to quantify how close we can get to the target. And if we use dynamic programming for this, it's harder to get a theoretical guarantee on how close to the target we can get. But that said, it's not a bad idea to just get an approximation. So let's take a look at this idea that's somewhat similar to that idea. So what is this doing?
Let's see, it takes in the subset S, right? Let's see, then it takes the number n, which is how many integers are in there, right?
Mm-hmm.
And then it takes, let's see, the target sum t. Fascinating.
So I'm going to go back and kind of describe all of this at this point. Let's see. Yeah, let's just go through. Actually haven't animated the last couple of slides for this. Oops, something that I should have caught. But yeah, so we're going to start with a list that has an integer 0 in it. Then we're going to go through every box, and we're going to say, let's merge the list from the last one with the list of what contains the next box, and we're going to remove every element in the list that is greater than the target. If we do that for every box, we're basically looking at adding each box to every sum that represents the subset of some number of boxes that came before it. Then the largest element in that list would be guaranteed to be less than or equal to t, and also be the composition of some number of boxes. Let's look at, this would solve the problem, but it again is complex. The size of this list will grow and grow and grow and grow to potentially be exponential in size. But if we wanted to approximate this, rather than having worst case exponential number of values in this list, we could trim this list and say, rather than storing every possible combination, let's just store every possible combination that is relatively close or sorry, relatively different from each other, such that close values in this list get removed because they are approximated by another value in this list. So let's trim the list after every loop of the algorithm on the last slide, such that, say we have this initial list, 10, 11, 12, 15, 20, 21, 22, 23, 24, 29. Those are the weights of the boxes. A trimmed set at this point would say, well, 11 is within 10% of 10, so we're going to remove it. 12 is not within 10% of 10, so we're going to keep it. 15 is not within 10% of 12, so we're going to keep it. 20 is not within 10% of 15, so we're going to keep it. 21 is within 10% of 20, so we're going to trim it. 22 is within 10% of 20, so we're going to trim it. 23 is not within 10% of 20, so we're going to keep it. Then we would trim 24 and not trim 29. The idea is there's separation now between every value that's in the list. And then we could add on the next box at the end of this. And we're guaranteeing with this trim some guarantee about the maximum size of this list. How many elements can possibly be in this list if every element has to be more than 10% away from the prior element in the list. We get a guarantee now about how many elements are in this list. We can't just continue to add more and more and more and more elements to this list with it growing exponentially. That concept makes sense? The exponential complexity part of this problem comes from the number of elements in the set. And when you add a new box, you have to add the weight of that box to every single element in the list to get another element that we will be adding to the list. So if each time we trim that list, we're guaranteeing we're placing some other upper bound on the size of this list. Any questions on that idea? It does make it much less accurate, absolutely. But it makes it less accurate in a way that we can quantify. And in fact, that's what the next and last slide of the slide deck is going to show, is exactly what that, how can we quantify how much less accurate it is. In the worst case, how much worse or less is the closest value to t than the optimal closest value to t? Since it will take exponential time to compute the actual closest value to t, this will give you an approximate closest value to t in a way that works. I'm actually going to quickly take, we're loading a single box. No. So we would start with just 0, like we had in the last slide. We start with the list with just the number 0 in it. And then we would take the first box. Maybe that first box has weight, I don't know, I'll use this, has weight 10. So we would say 0 plus 10 is 10. And now the new value of this set would be 0 and 10. If the next weight of a box is 11, we would then say we're going to take the 0 and add 11 to it, giving us, we would keep the 0, we would keep the 10. We would add 0 plus 11 to give us 11, and we would add 10 plus 11 and give us 21. And then we would loop back around and consider the next box. We would run the next box through every element of this set and compose the next set out of that.
This is a different version of the Fibonacci sequence.
Kind of. It's very similar. You take everything from before rather than just the last two and compute the next set based on the weight of the next box and the sum of every possible combination that we've seen so far. And since it's a set, if we ever have a duplicate, we ignore the duplicate.
Still.
But in the worst case, there are still going to be an exponential number of these at the end of this process, because for each box, we're looking at every combination of the set of boxes that came before it and potentially adding up to that many more elements to the set in a way that will not scale well. As there become more and more boxes, the size of this set grows and grows and grows and becomes millions, billions, trillions of elements.
Yeah, very good point.
So an approximation algorithm says we're going to trim the list of relatively similar sums that we've seen so far so that this doesn't scale. Basically, we see exponential decay in the accuracy of this over time. And I'm quickly going to animate this last slide because there's something on here that I want to take a little bit of time to, and of course you can see it. Great.
No, they can't, we're blind.
Just.
There.
I was gonna say, you probably should turn off the projectors for 1 second.
So, yeah, it's going to be the trace. I want people to go through the trace for this. So the approximation algorithm for this says that we're going to use an approximation parameter epsilon. And that approximation parameter is, according to the last example, it was the 10%. We trimmed everything within 10% of the last element of the list. That approximation parameter gives you what that percentage is. The output, the book calls Z star, so we're going to go with Z star. That is a value within some factor of the optimal solution, and that's 1 plus epsilon. So it gives you something like if epsilon is 0.4, then we guarantee that the answer is within 40% of the optimal solution. 40% is a big swing. Like you don't want, if the truck can hold 1,000 pounds, within 40% says we may end up loading this with 600 pounds and call it good. That's not a great solution. So we use a smaller value than that when we pass to trim, because this leads to compounded inaccuracy. If each time we're getting rid of elements that each time the inaccuracies propagate to the next set and then to the next set and then to the next set with an additional inaccuracy for each of those values. So the more boxes we have, the more it's like exponential decay. If you multiply something by 0.9, the first time you do it, it's 90%. The next time you do it, it's 81% of the original. The next time you do it, it's 72 point something percent. And this decays depending on the number of times you multiply 0.9 to the n. The larger n is, the smaller that value is. So you get exponential decay on the accuracy of this, the more boxes we have to consider. So we use a smaller value that we pass to trim, which is epsilon over 2 times the number of boxes. So the example we have here is the set that it contains. We have 4 boxes. They are 104 pounds, 102 pounds, 201 pounds, and 101 pounds. So n is 4. The truck has a capacity of 308 pounds. We're going to use 0.4. So when we pass to trim, 0.4 over 2 times the number of boxes, 8, gives us 0.05. So from there, let's go ahead and trace the algorithm. So here's the algorithm for you. What does this output as the best answer to which boxes we should, how many pounds can we load onto this truck? And unfortunately, we're kind of running out of time. So I'm just going to go over that trace. So we start with line 1. We start with just a set with the sum 0 in it. Then we're going to add the first box, the 104. So we're going to add in, we make this new list, 0 plus 104 is 104. We union that into the set. Line 4 says we're going to trim that. 104 is not within that small value of 0, so we keep it. We move to line 5, that's going to remove everything that is larger than 308, the target. Then we loop back around to consider the next box, 102. we're going to add 102 to each of the elements in the list. 102 plus 0 is 102. 102 plus 104 is 206. Then we're going to trim from that. And that gets rid of the 104. It's within that 5% of 102.
Makes sense.
So 104 goes away. Then we also remove every element that's greater than 308. There's nothing greater than 308. So we loop back around to consider the next one. We're going to add 201 to every element in the list. That gives us everything we see here in line 3. Then we go through the trimming process and we see that 206 is within 5% of 201, so 206 gets trimmed, and that's it. Then we remove everything greater than 308, which is the 407, that goes away. Then we loop back around to consider the last box. 101, we're going to add 101 to every element in the list, then trim, then remove everything larger than the target. Then we finally get to the end and return the largest value in the list, which is 302. And that is our approximate solution to the best weight that we can add. Note that we probably should have been storing some kind of backtrace with this so that we know which boxes to put on the truck. We've just come up with an answer here. We can have some subset of boxes that are 302 pounds.
Why, you know what, please do.
So which should we do? We need a backtrace to do that, but we at least see that we're within a pretty solid 6 pounds of the target. And in fact, what is the optimal value here? If you're looking at these, what boxes would you load on in order to get to 308? 104, the 102, and the 101 would get you to 307. But we're within 5 of the optimal value. And we would see that this actually gets you to within a guaranteed, unfortunately, 40%. That epsilon is the worst case for this, which is still not great. But in practice, we outperform the worst case pretty frequently. So it ends up being a useful, decent approximation. Yeah, we can come back to this on Monday before we dive into interviewing.
At least I was confused at first, but now I actually understand the meaning down in my phone. Nice.
We'll in fact summarize this and then have a very important unit on interviewing, preparing for interviewing. Because that is what, if you're not already thinking about and doing it, it's something you should be thinking about and doing.
I've been in a few interviews regarding trying to get a job. But I tend to just be a lot more honest about myself. Just kidding. It's not really. But I am trying to offer more or less.
That's fair. That's a good way to end up at a job that will appreciate who you are. If you oversell yourself, that's going to be a future problem.
I haven't exactly gotten any jobs that approach yet, better than mine, so we just over exaggerating.
Yeah. Okay. Have a good weekend. I have office hours starting now. If anyone remotely would like some office hours as well, just send me a quick email and I will be able to handle some Zoom office hours.
Well, this is a pretty full problem though. Yeah, I think next week I am most likely going to. Well, what's my thing? Oh, just